And we last left sort of talking about delta G, and delta G is basically Gibbs free energy. Um, and basically, what that is, as we talked about, is basically energy available to do some type of work. Um, and we saw really a few different ways to calculate delta G. Um, we saw just like kind of delta H, delta S, that you can take delta G is basically our delta G of our products minus our delta G of our reactants. And this would be a situation where if you're just sort of given an equation and you want to calculate the delta G, you would go basically to the table and you can look up those values. So remember those values in the table are what are referred to as delta G of formation, so delta GF. And those are basically table values. And again, you would find what you're looking for in the correct state. You would also need to take into account the coefficient and from the balanced equation and multiply that as the moles by each one, and basically take your products minus your reactants when you sort of add up all your products together and all your reactants together. Now, when we do calculate delta G, and if we do get a delta G that is negative, that does mean that the reaction is going to be spontaneous. If we get a delta G that is positive, it means the reaction will be non-spontaneous in that particular case. Another very common way that we can sort of calculate delta G is this reaction here that we sort of used. And that is the delta G is equal to the delta H minus T delta S. Delta H being our enthalpy, which is our heat of our reaction, delta S being our entropy, and T being our temperature in Kelvin. And we could use that equation. And again, as we talked about, we're going to see a couple other ways as well here to calculate delta G in just a second. But you kind of want to choose the equation that sort of fits the information that you're given. So if you're given, a delta H value, a delta S value, then you would want to use perhaps this equation here with the H and the S. We do want to make sure, as we talked about last time, that you do watch units. So again, the delta H is usually in kilojoules. The delta S is usually in joules. So you want to do that conversion. And again, it doesn't really matter which one you sort of convert it to. In the end, though, in terms of units, delta G is also usually in kilojoules. So we usually have that in kilojoules as well. In addition, temperature does need to be in Kelvin here for everything to cancel out. So if you're given the delta H, the delta S, you can use this really to sort of calculate the delta G pretty quickly. And again, that negative or positive will tell you whether or not that reaction will be spontaneous. We also saw that we could use this equation in a situation, perhaps if we did calculate the delta G using this equation, and we see that it is a positive number, we could use this equation to figure out at what temperature it does become spontaneous. And remember that that happens pretty much at a negative delta G. So if we put delta G equals 0, we then can solve for T, and that would give us the temperature at which this reaction would become spontaneous. So I think we looked at one where, it wasn't spontaneous at 25 degrees Celsius, but when we do head over to about 835 degrees, we do start to see it becoming spontaneous, which is obviously a very high temperature. We also saw that you can use this equation and really not even numbers, and either whether the H is positive and the S is positive, or the H is a negative value and the S is a negative value, to help determine, what you would predict it to be, either spontaneous or non-spontaneous, and really what temperature you would need for that to occur. So remember that, for example, if delta H is positive and delta S is negative, no matter what you do, you're always going to get a positive number for delta G. So the reaction will be non-spontaneous at all temperatures. If you have a positive delta H and a positive delta S, the reaction will be spontaneous at really high temperatures. And again, that's because the back end there needs to get higher than the delta H value to become negative. So we talked about that as well. And lastly, we really finished up sort of, I think, talking about sort of phase changes and entropy and all that. Remember, as we go from solid to liquid or liquid to solid, again, in terms of the heat or energy, the delta H, that's the delta H of fusion. And that's the energy required to change a substance from either solid to liquid or liquid to solid. It is the same number regardless of which way you're going because it does happen at the same temperature. The only difference is the sign. So one's positive, one's negative. Positive being the endothermic process of solid to liquid, negative being the exothermic process of liquid to solid. And same thing as we transition from liquid to gas or gas back to liquid, that's the delta H of vaporization. Also, the same value, just a different sign depending on which way you're going. Because again, that also does occur at the same temperature. And because that's an equilibrium process, because it occurs at the same temperature, our delta G in that equation that we're looking at here in the middle of the screen will equal zero, because remember, delta G is zero at an equilibrium type process. And that allows us to rearrange this and solve for delta S like we did here. And this delta S, for example, could be the delta S of vaporization. And that's basically the process where we go from liquid to gas. And as we see here in this example, we ended up with a positive number, which also makes sense. Again, as we're going from liquid to gas, we would expect an increase in the disorder, and we would expect the delta S value to be positive, which it was here. Really, as we talked about as well, if we went the opposite direction, sort of sublimation, not sublimation, I'm sorry, condensation, going from gas to liquid, really the only part of this calculation that we're looking at that would change is the delta H of vaporization. Delta H of vaporization in that case would be a negative value as it goes from gas back to liquid. And that would then turn our delta S into a negative value. And that also would make sense in that process because we're going from gas, which is a lot more disorder, to liquid, which is a lot more order. And we would expect a negative delta S in that particular case. Any questions on any of that stuff? I think we talked about there last time. Okay. So continuing on with our sort of Gibbs free energy, again, there's a couple of other sort of equations that we use that involve it. And let's take a look at each of these and sort of talk about them. Excuse me. Really, the top one here is one equation that you should be familiar with. And we'll talk really about this bottom one here in just a second. But this top one here is our delta G equals delta G naught plus RT natural log of Q. So let's talk about kind of what these two guys are. Here we have just regular delta G, no naught, no little circle on it. And we do have obviously our delta G naught, which is over here. So our delta G naught, again, when you see that little kind of circle on top, which is the naught, is sort of like standard conditions. So basically, you could calculate this by taking delta G of our products minus delta G of our reactants, like we talked about. So this delta G at the beginning, you could kind of think about it as being maybe non-standard conditions. So what does that mean? So if you remember standard conditions when we talk about sort of thermodynamics and just in general, usually refers to a temperature about 25 degrees Celsius. It refers to a pressure of 1 atmosphere if we're dealing with gases. In terms of concentration, usually 1 molar. So these are sort of standard type conditions. And these, again, as we talked about last time, are really what you find in sort of tables and table type values. And if something is not one of those things, so perhaps the concentrations aren't all 1 molar in the guy, or maybe the pressure, if you're dealing with a gas, is not 1 atmosphere, maybe the temperature is not 25 degrees Celsius. It will affect, say, the delta G value, and that's what we get here. So this is a good way to sort of think about it, is sort of delta G when we are not at perfect sort of standard conditions, table type conditions. R is our gas constant, and it is the gas constant that involves energy. So it is not the one that we use in the ideal gas law. This is our 8.314 version of it. T is our temperature that does need to be in Kelvin. And Q is our reaction quotient. So remember that Q is the same Q we've seen many times at this point, and it is just like you calculate K, which is our products divided by our reactants. Obviously, you use the coefficients as the exponents, just like you would do before. So this delta G here is sort of, again, a way you could kind of think about it is delta G under sort of non-standard conditions. So again, something there is not in that sort of textbook standard conditions. Now, if we take this top equation and we do hit an equilibrium condition, at equilibrium, our delta G would equal 0. And we would no longer be talking about Q. We would be talking about the equilibrium constant. And this reaction or this formula becomes delta G naught equals minus RT natural log of K. And these are still the same guys as above. So R is our gas constant at 8.314. T is our temperature in Kelvin. And K is our equilibrium constant. So again, here we have a number of different ways that delta G can sort of be calculated. We're up to like 4 different sort of equations or formulas that have delta G in it. Again, delta G products minus reactants, which is the one you would want to use. Again, if you're just given an equation and nothing else, we have that delta G equals H minus T delta S. And again, you would want to use that if you have an H and an S value given to you. We have our delta G here equals delta G naught plus RT natural log of Q. You would want to use that if you got some concentrations, pressure, something like that, that's not standard conditions given to you. And lastly, here we have our delta G naught minus RT natural log of K. This would be the one that you would want to use when anything's involving the equilibrium constant. So these are the sort of the ways you want to kind of think about these different formulas and how to choose which one to use. The simplest way to do it is really just to think about the information given to you and kind of pick the one that, you know, has that information in it. A couple of places where people screw up is right here on this one. They always want to subtract, so it is a plus here. And the other thing people screw up is they either don't put the negative here as well. So again, those are 2 common places on these formulas where people kind of mess up as they go through it. Excuse me. Any questions on that there? Okay. So if we look at this equation, just like the other ones, we could really sort of focus in on and really make some predictions as to what we would expect to happen here. And really, because this one does have K involved, the equilibrium constant, really from our knowledge of K, we could pretty much make a pretty good prediction. Just like we know before, if we have a large value of K, that should mean that we mainly would have products at equilibrium, which mainly should mean, obviously, that we are going towards the product side, which means this reaction should be spontaneous, and we should expect a negative delta G. And we would obviously have more products at that point. If we had a small value of K, just like we know before, that means that when we reach equilibrium, we should mainly have reactants, which means this reaction is really not going to the right, but going to stay to the left. And that means that it would be non-spontaneous the way it's written, and we would have a positive delta G. And that would mean that we, again, have mostly reactants here. If it's equal to 1, natural log of 1 is 0, so our delta G would equal 0. You have sort of a equally chance of reactants or products in this case, again, because it's basically at 0. So the nice thing about that sort of guy is that you can really sort of figure it out based on the K value. It always basically works the same way. So again, a large K means we should have a negative G. Small K, we should have a positive delta G value in that particular case. All right, so why don't you give this a try here? Calculate the equilibrium constant, Kp, for the following reaction. On the bottom is the delta G value for O3 that you could find in the table. So take a minute or two and see what you come up with. Okay, so let's take a look here. So again, like I said, there's whatever we counted there, four different equations or so that involves delta G. So in this particular case here, we are trying to find K, which is an equilibrium constant. So that should point you to the only really one that had uh, K in it, which is this one here. Our delta G naught equals minus RT, natural log of K. R is our gas constant, which is our 8.314. T here, we do need to convert into Kelvin, so we'll add our 273 to it. So at this point, we do have R, we do have T. We are looking for K. So we do need to actually find our delta G naught. So our delta G naught would come from the table here of our products minus our reactants. And in this particular case, delta G naught would equal our products, which is O2. And again, remember that delta G for anything in a sort of standard state is going to be 0, minus our O3, which is 163. And we do need to take 2 times 163.4. And that will get us minus 326.8 kilojoules for our delta G value that we have here. Any questions on that so far? We do see that this reaction, it has a negative delta G, so we would expect it to be perhaps spontaneous. We now have everything we need really to solve for K. And if we do that, I think I got an empty spot here. I do. Okay, perfect. So again, we have our delta G naught equals minus RT natural log of K. That means the natural log of K would equal delta G naught divided by RT. And there's also a negative there as well. So putting in our numbers here, that's going to give me a negative 326.8. I am going to multiply it by 1,000, and that's going to convert it into joules. Again, we have R, which is in joules. We have delta G here, which is in kilojoules. So again, you got to do some type of conversion there, whichever way you want to go. So I'm going to do it into joules here when I'm doing it. They're going to divide that by our R, which is 8.314 joules Kelvin mole. And that's exactly why we had to do that conversion right there. And we got 298 Kelvin here. And if we do all that good stuff, we get a natural log of K is equal to, what we got there? About 131.9. To get rid of our natural log, we need to take really E of both sides. So we would take E of this guy and we would take E of this guy on your calculator. When you do the E on the other side, basically these two cancel and you're left with K. And when you do it on that side, you end up with looks like 1.9 times 10 to the 57 there in terms of our equilibrium constant. Any questions on any of that math there? So does this sort of make sense based on what we saw? Well, again, our delta G naught was negative, which means this reaction should be spontaneous, which means it should be heading to the product side, which means we should have a large value of K. All those things do make sense here. I would say that's a pretty large value for sure in this particular case. Any questions on that calculation? Okay, why don't you try the next one then? See what you come up with here. So we want to calculate the delta G naught for the following if the KSP is 1.7 times 10 to the minus 6. So see what you come up with. Okay, so on this one as well, again, if we look at it here, we are given a KSP value. So remember, no matter what type of K value you're given, they're all essentially equilibrium constants. So again, here, our guy that involves the equilibrium constant would be the proper one to kind of choose. And we really have everything on the right-hand side here. So we really just need to kind of plug it in. And if we do that, delta G naught is equal to minus our R value. Our T value also, again, needs to be converted into Kelvin. So we're going to add 273 to this guy. And that's going to be the natural log. Again, doesn't matter what type of K value it is, it's still a K value. So we're going to go 1.7 times 10 to the minus 6. That is going to give us a delta G naught of 32914. The units here would be joules, or if we kind of clean it up a little bit, about 32.9 kilojoules would be our answer here. First off, any questions on the calculation here? We could also see if it does make sense. So we are definitely starting with a KSP, which we know just from our experience earlier. KSP are typically for things that are insoluble, which means they typically are small values of K, which this is, which means we typically should be over here at the reactant side. And that would mean that our delta G is probably going to be a positive number, which would indicate that this reaction is really non-spontaneous, really hanging out more on the reactant side, which is what we would expect here for something that has a KSP that's pretty much insoluble. So again, all these sort of values do make sense. It's a really good idea to sort of think about those things when you get an answer, because there's a lot of sometimes the negative values and things like that, or negative signs that people maybe sometimes forget or put in. And again, you want to kind of think about it. Doesn't make sense sort of logically. Any questions on that particular one there? All right, one last one here, I think. So let's take a look. Delta G naught for the following is 2.6 at 25 degrees. In one experiment, we got the partial pressure of H2 4.26, partial pressure of I2 0.024, and partial pressure of HI 0.23. Calculate the delta G for this, and the equal sign is just an extra afterthought there. All right. So take a couple minutes to see what you come up with on this one. Okay, so let's take a look and see how we're doing. Now, in this particular problem here, when we look at it, we're given a few pieces of information. We're given delta G naught is 2.6 kilojoules. We do have the temperature that's 25 degrees Celsius, which is basically 298 Kelvin. And we do have some partial pressures given to us. So we got partial pressures of everybody here, and we're looking for a delta G. So again, this one really should point you to the one that has all those things in it, which is our delta G equals delta G naught plus RT natural log of Q in this particular case. In this particular case, they did give us our delta G naught. If they didn't give us our delta G naught, we would go to the table and do products minus reactants and look up the values to do that. R is obviously a constant, so we have that. T here we also have, and we do need to use Q here. Again, we're going to use Q because if we look at these pressures are not 1 atmosphere. So remember, standard pressures would be 1 atmosphere, which obviously this is not. So this is really the part of the problem here that is sort of the non-standard conditions, is those pressures that we see here. The temperature is still 25, so that's all good. But really what it is, not making it sort of under standard conditions, is that the pressures of each of those gases are not 1 atmosphere. So we do need to calculate Q, and a reminder that Q is done the exact same way that we do calculate K. So in this particular case, it would be the partial pressure squared of HI divided by the partial pressure of H2 times the partial pressure of I2. So that would be how we would calculate Q. We do have all of those values given to us in the problem, so we could put them in there. And what that really means is essentially we do have pretty much everything on the right-hand side. So we just need to kind of plug it in there and get a number. So let us go and look at that here. So our delta G equaling our delta G naught, again, plus RT natural log of Q. That's going to give us 2.6. Again, here I need to do some type of conversion. So I'm going to multiply it by 1,000 to convert it into joules. And again, the reason for that is R is in joules. So again, if you don't do that conversion of one of them, either convert R to kilojoules or convert G to joules, you are going to be off by that factor of 1,000. So you want to make sure you watch that there. We're going to do 8.314 joules, which is our R. We're going to do our temperature, which is our 298. We're going to go natural log. Again, our, excuse me, products over reactants. So that would get us 0.23. Again, we need to square it, divided by 4.26 and 0.024, I believe. I didn't mess that up there. I think that's right. 0.024, 0.23. That's good. All right. So if we kind of clean up everything there on the right-hand side, we're going to take 0.23. We're going to square it. We're going to divide it by 4.26. Hit equals divided by 0.024. Hit equals, take the natural log of that, times it by 298, times it by 8.314. We are then going to take 2.6 times 1,000 and add it to what we got there. And doing all that good stuff there gets us something like 967. The units here would be joules in my case, because I converted to joules, or since delta G is typically in kilojoules, 0.967 kilojoules in this particular case. Any questions on that there? Couple of things that we do see, again, our delta G under sort of standard conditions is 2.6 kilojoules in the positive direction. And even under these non-standard conditions, still a positive delta G, which means, again, this reaction is going to be non-spontaneous, which basically means we should expect some more reactants in this case and should be heading kind of in this direction towards the reactant side. Again, because our delta G here is positive. Any questions on any part of that calculation, where any numbers came from, are in general for thermodynamics? That should wrap up this chapter. Okay. All right, so that should wrap up this chapter about thermodynamics. Again, we talked about delta H a little bit in here as well, with delta S, delta G. And again, we were looking at whether or not a reaction was spontaneous or non-spontaneous. And as we talked about many times, again, if a reaction is spontaneous, doesn't mean that it occurs super fast. Could occur fast, could occur slow. It just means under those conditions, we would expect that reaction basically to take place. All right, then we're going to move on to chapter 17, which is some electrochemistry. So just give me a second here to kind of get it all arranged. Hopefully my computer here will cooperate. There. Okay, so we're off to chapter 17, which is electrochemistry. And let's do that there. And do that there as well. Okay. So in this chapter, we're really going to talk about galvanic cells and some electrochemistry with that. In the beginning here, we're going to go over redox reactions, how to balance redox reactions, again, oxidation numbers, just to make sure everybody is sort of on the same page, depending maybe on your experience there in Chem 50 or not. You might have did a lot of this, maybe did a little bit of this. You should have done at least something of it, I suppose. But just to make sure, again, everybody's sort of on the same page moving forward in this chapter here, we're going to kind of cover some stuff. So if you've kind of seen it before, I apologize, but hopefully it'll be a good review. If you haven't seen it before, these are things that you do need to know, obviously, how to do, especially in this chapter and when you're dealing with redox sort of reactions. All right, so let's take a look at this here. So an electrochemical process involves basically what are referred to as redox reactions. And redox basically means oxidation and reduction reactions. And when we talk about oxidation and reduction reactions, we talk about what those mean. So typically, if something goes through an oxidation, it typically will lose electrons. If something goes through a reduction, as it says on the bottom there, it will gain electrons. And there are other definitions of oxidation and reduction. So, for example, oxidation could also mean that you gain oxygen as you go from reactants to products, or you lose hydrogen as you go from reactants to products. So those are two other sort of definitions of oxidation. And reduction would be sort of the opposite of that. You would lose oxygen as you go from reactants to products, or gain H2 as you go from reactants to products. And really, in organic chemistry, if you're off to organic chemistry after this or whatever it may be, you'll see those definitions used a lot. For us, we don't really use too much of those definitions here. It does pop up occasionally. We more use this sort of gaining or losing of electrons. Some people remember that as Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You can use both. You don't have to choose. Put Leo the lion on the oil rig and he goes grr. So you don't have to actually choose one. You could use either one. So what does that really mean? What we're talking about here in this chapter, and we will be talking about in this chapter, is these things always occur together. So if something goes through an oxidation, there's usually something that will go through a reduction reaction. And as that occurs, we could use those electrons really to do some type of work. So as we will see, is kind of similar to like a battery, right? Electrons go out, go around, and it basically will power a device. And sort of the same idea. We could use those electrons as they flow really to do some type of work. And we can also use it to do some non-spontaneous process, help that occur as well. Now, what does it mean when something gets oxidized or something gets reduced? Sometimes people have a really hard time sort of figuring out, is this thing being oxidized? Is this thing being reduced? So there's sort of a simple way you could kind of do that. And it's just a basic sort of number line approach. And there's kind of like zero and positives usually to the right, negatives usually to the left numbers. And when things lose electrons and go through oxidation, they obviously lost electrons, which means they have more protons and they're more positive. So if you see that your oxidation state is becoming more positive or moving in that direction, that thing is going through oxidation. Opposite is true when something gains electrons and becomes reduced. It obviously gained electrons, became more negative. So if you see yourself move in terms of the oxidation number to the left-hand side towards the negative side, that is something that is going through reduction. So how can we figure out if something is going through oxidation or reduction? We could look at oxidation numbers or oxidation states. Things in its natural state have an oxidation state of 0. So when we look at this reaction here, magnesium is all by itself, uncombined. It has an oxidation number of 0. The oxygen, the O2, is also how it comes naturally. It's uncombined. It also has an oxidation number of 0. These two guys really don't gain charges until they actually come together. So when the magnesium, the oxygen do come together, that is when the magnesium gains its +2 charge, and that's when the oxygen gains its -2 charge. So how the sort of number line works to decide is something being oxidized or reduced, we basically could look at something like magnesium. It started at 0 and it ended at +2, which means it is moving in this direction. And that would tell us that the magnesium here is going through oxidation. While if we look at the oxygen started at 0 and ended at -2, which on the number line would be moving in this direction. And it is moving to the left there and becoming more negative, which would tell us that the oxygen here is going through reduction in this case. So that's a very simple way you could kind of figure out, what is being oxidized, what is being reduced. If you have sort of trouble with that, that's a very easy way to sort of figure it out. We could take this overall reaction and split it up into what are referred to as half reactions. And in redox reactions, there's two types of half reactions. One is an oxidation half reaction, and one is a reduction half reaction. So as we just determined, our magnesium is an oxidation half reaction. So we have two magnesiums. They both are going to lose 2 electrons each for a grand total of 4 electrons. And when we write a half reaction where we see electrons on the product side, like they are being lost, like they are being given off, that is what is referred to as our oxidation half reaction. So in an oxidation half reaction, the electron should always be on the product side. And that is different than in a reduction half reaction. In a reduction half reaction, something is gaining electrons. And the oxygen here is going to gain those 4 electrons, and it's on the reactant side. So when you write a reduction half reaction, the electrons should always be on the reactant side like they're being gained. And here, each oxygen gains 2 electrons, and we get our oxygen with a -2 charge on the right-hand side. These are what are referred to as half reactions because essentially, if you add them together, what should always happen is the electrons should always cancel out completely. And that is because whatever number of electrons somebody loses should be the same number of electrons that somebody gains. And if you keep everything on the left-hand side, everybody on the right-hand side, and if we add it together, we end up with the overall reaction, because these two ions will come together to make two magnesium oxides. So in a half reaction, we split it up into the oxidation half reaction and the reduction half reaction. And we should always, before we add them together, like I just did there, we should always make sure that both half reactions have the same number of electrons in them. If they don't, then you need to multiply by a number to get the same number of electrons, because the basic idea of a redox reaction is, like I said, somebody will lose a certain number of electrons, and there's sort of conservation there. All those electrons will be gained by somebody else. So each half reaction, before you add them together in sort of a basic one, you want to make sure same number of electrons on each half reaction. Any questions on that there? That's sort of what we just did. Here's another example here. If we look at these guys, if we look at our calcium here, again, our calcium is going from 0 in terms of its oxidation number, as it's by itself uncombined. Oxygen here is 0 as well. When these two come together, this is when our calcium gets the +2. This is when our oxygen gets the -2. Again, if you're not sure, if you look at your number line here, we look at the calcium, started at 0, ended at +2, going to the right, which means the calcium is going through oxidation. If we look at the oxygen, started at 0, ended at -2, going to the left, which means this is going through reduction. So again, a very simple way you could kind of figure that out. By the way, as you probably should know, probably from Chem 50 and maybe even Chem 40 as well, metals, right, are typically the ones that lose electrons. So when you have a metal and a non-metal together, that is usually what should happen. Our metal should lose electrons and go through oxidation. Our non-metal should gain electrons and go through reductions. Again, we could split this off into balanced half reactions here. We have 4 electrons in each on opposite sides. This is our oxidation half reaction, as our electrons are on the product side. This is our reduction half reaction, as our electrons are on our reactant side. Again, you could keep everything on the left-hand side, everybody on the right-hand side, and the arrow is kind of like an equal sign. So if you subtract 4 electrons from both, they will cancel each other out. And we keep everything on the left, everything on the right. Again, our calcium ion and our oxygen ion will come together and basically make our calcium oxide. Any questions on that there? Now, something that also sometimes will confuse people when we're talking about sort of redox reactions is the idea of oxidizing agent and reducing agents. And those things are different than what is being oxidized and what is being reduced. So when we talk about reducing and oxidizing agents, the oxidizing agent is the substance that actually is being reduced. So why is it called that? Well, if it is going to be reduced, that means that it does need to gain electrons. And in order for it to gain electrons, something has to lose electrons. So it causes something else to lose electrons, and that is why it is known as the oxidizing agent. Vice versa as well, the reducing agent is the substance that gets oxidized. And what that means is if it gets oxidized, it will lose electrons, which means somebody will gain electrons and go through reduction. So it is known as the reducing agent. Simple way to remember that is if you're asked about the reducing agent or oxidizing agent, it is basically opposite of its name. So the oxidizing agent is the guy that is going through reduction. The reducing agent is the one that is going through oxidation. And again, you don't want to get that confused with what is being oxidized and what is being reduced. So again, there is a difference between those two things. So if we look at our couple of examples there earlier, our calcium, which is going through oxidation, our calcium here would be our reducing agent. Our oxygen, which is going through reduction, would be our oxidizing agent. Again, it is causing the oxidation of calcium, and that's why it's called that. While calcium's our reducing agent, it is causing oxygen to be reduced. Your oxidizing agent and your reducing agent are always found on the reactant side. Yeah. So these guys are always found over here on our reactant side. If we look back in the previous example before this one, our magnesium again was going through oxidation, which means this is our reducing agent. Our oxygen here again was going through reduction, which means this is our oxidizing agent. So again, those guys are always sort of found on the reactant side, and it is really the opposite of the actual name. Any questions on oxidizing agent, reducing agent? I mentioned this a little bit earlier that sometimes, and especially you'll see a lot more of this again if you take sort of organic chemistry, but you can use those sort of other definitions of oxidation and reduction. So for example, as I mentioned before, oxidation can mean that you gained oxygen as you went from reactants to products, or lost hydrogen from reactants to products, and reduction means that you lost oxygen from reactants to products or gained H2 from reactants to products. So if we look at something like this, sometimes it might be easier to just kind of look at that. You know, for example, if you looked at the carbon here on the left-hand side, no oxygens, carbon on the right-hand side gained some oxygens. So that would tell you that the carbon here went through oxidation. And because the carbon went through oxidation, that means that the carbon is our reducing agent in this particular case. By default, the good thing about redox is if you can figure out one by default, that means the other guy is the other thing happening. So this guy would go through reduction, and this would be our oxidizing agent. The good news is that in this particular case, we do have a metal involved, which makes it easier to kind of go with our normal definition of oxidation reduction. The tin here has a +4 charge. The tin on the other side has 0 in terms of its charge. So if we look at our number line in terms of tin, the tin started at +4, which is over here, and it ended at 0, which is moving in this direction. And again, that tells you that it is being reduced or going through reduction. So in this particular case, you could have just used our basic definition with tin and figured out by default that the carbon was going through oxidation. Or again, you could use that other definition as well. You also see that the tin lost some oxygen as it went from left to right there, which is again a definition of reduction as well. So like I said, most of the time we're going to probably be seeing the oxidation numbers. Occasionally it might be a little bit easier sometimes, especially when you have a lot of non-metals sort of involved. A lot of times it's easier to kind of look at oxygen gaining or non-gaining, but most of the time we could use oxidation state or oxidation number to sort of figure it out. Any questions on that? Now, how do we know or sort of assign oxidation numbers or oxidation states? So let's talk about the rules for that. And these are the general rules that we want to follow when we're assigning oxidation number or oxidation state. So they're sometimes referred to as the same thing. Oxidation number is the same thing as oxidation state. And it's basically the charge the atom would have in a molecule or an ionic compound. It pretty much all the electrons were transferred. So the first rule is one we talked about a little bit here. All the free elements in their uncombined state, the way they sort of naturally come, will have an oxidation number of 0. So that's why we have something like sodium metal, potassium metal, lead metal, even hydrogen gas, oxygen gas, nitrogen gas. Anything in this sort of natural uncombined form will have an oxidation number of 0. If we have a monoatomic ion, the oxidation number is basically the charge. So, things like lithium is +1. If you had like iron 3 chloride, the iron here would be +3, just like we just saw there. If you had tin 4 oxide, the oxidation state on the tin is 4 +4. So things with their kind of normal charges and sort of normal, either by themselves or maybe in an ionic compound, will typically be the same as the charge. The oxidation state of oxygen is usually -2. And that's really a good place to start. A lot of things in redox reactions involve oxygen, or oxygen's involved somewhere. So most of the time it is going to be -2, and most of the time that is a pretty good place to start. The one exception is if it is actually peroxide. Peroxide is O22 minus. It's a polyatomic ion. And in that particular case, oxygen would be -1. So how do you know if it's like regular oxygen or peroxide? Usually, I won't say 100% of the time, but a lot of times there's like that extra kind of 2 present. So you got that extra 2 involved in the formula, and it's usually peroxide. Probably 9 times out of 10, it is going to be just regular oxygen and -2. But again, something like hydrogen peroxide would be -1 in that particular case. When we look at the oxidation number of hydrogen, it is usually +1. The only time when it's really not +1 is when it comes after like a metal. So like LiH, that is hydride, which means it would be -1 in this case because the lithium is +1. So most of the time hydrogen is going to be +1, but again, if you see it after a metal, it will be -1. Group 1 is always +1, group 2 is always +2, and fluorine is always -1. Now, when we add up all of the oxidation numbers for something, it does need to equal the charge on either the ion or the molecule. So if the overall molecule is a 0 charge, when you add up all the oxidation numbers, all the oxidation states, it should equal 0. If the overall thing is an ion, like -2 or something like that, when you add up all the oxidation numbers, it should equal -2. Also, it's important when you give an answer for oxidation number or oxidation state that you also include the charge. So you shouldn't just write 1. You should either write +1 or -1. Again, you shouldn't write just 2, +2, -2. So you do need to include the charge as an important part of understanding really what the oxidation state is. So just don't write the number. Make sure that you do write the charge as well. So if we look at something like HCO3 minus, so when you got a situation like this, you got 3 elements together, 3 sort of nonmetals together, and especially if you have oxygen, a really good place to start with is usually the oxygen. And in this particular case, the oxygen would be -2. There are 3 oxygens for a grand total of -6. Then you usually should go kind of to the other side, leave the guy in the middle for the end. So if you go to the other side, hydrogen is going to be +1, would be its oxidation state. Now, this entire guy here, this bicarbonate, has an overall charge of -1, which means when we add up all of our oxidation numbers, it does need to equal -1. So at this point, what we got going is +1 and -6. So that's a -5. So to get us to -1 in this particular case, we should have a value of +4 for our carbon. That means if I take +1 and +4, that gives me +5. -6 leaves me a -1 left over. Now, when you want to report the oxidation states or numbers, you should report it like so. Hydrogen is +1. Again, the charge involved there. Carbon's oxidation state is +4, and oxygen's is -2. It is not -6. So that's a very common mistake that people make when they're given the oxidation number. They kind of give the grand total of all the oxygens there. But when you're asked to give the oxidation number or the oxidation state, it's basically just one element by itself, what it would be. So in this case, each oxygen is -2, even though there's three of them, that gives you a grand total of -6. Any questions on that there? All right, so you got some here, I think. Why don't you assign the oxidation states for each of the elements in each of those? So take a couple minutes here and see what you come up with, and then we will talk about it. Okay, so let's take a look here. So starting with our first one, we have Li2O. So starting here with oxygen, it would be -2. Lithium, which is group one, would be +1, and that's why there's two of them. So lithium would be +1. Oxygen here would be -2 in that particular case. Our next one is PF3. Again, fluorine going to be -1. And there's three of them, gives you -3. Overall charge here is 0. That means that the phosphorus here will be +3. So in this particular case here, the phosphorus would be +3 and our fluorine would be -1. So remember that again, oxidation numbers are not necessarily always the charge that we think about when we think about an ionic compound. So normally in an ionic compound, we think about phosphorus as being -3. In this particular case, because it's bound to three fluorines and it's actually sharing electrons here, it takes on a more positive charge than the negative charge it's associated with when it gains electrons when it's attached to a metal. So, again, when you talk about oxidation number states, it's not necessarily always identical to sort of the charge we think about with things. Again, the charge we think about with a lot of things on the periodic table is in an ionic compound situation where we have a complete transfer of electrons. And in a case when we're doing really covalent bonding, which is what's happening here, things take on perhaps a different sort of charge in that situation. If we look at nitric acid, HNO3, again, in a situation here where we have three, we want to start with perhaps the oxygen. Oxygen, again, going to be -2 here. There is three of them, gives us a -6. Going to the other side, we have hydrogen, which will be +1. Now, in this particular case, nitric acid has no overall charge. So to balance that out here, we have +1 and -6, which is -5. That means that our nitrogen here needs to be +5 because that's going to give us +6 and -6 equals 0. So for C here, we have H, which is +1. We have nitrogen, which is +5 in this arrangement. And we have our oxygen, which is -2. Again, here, same idea. Normally, when we think about nitrogen in an ionic compound, we think of it as taking on a -3 charge because it does. It gains 3 electrons. But in this situation, hydrogen, nitrogen, and oxygen, they are all nonmetals. They are all basically looking like this. And in this situation, because, for example, oxygen is more electronegative than nitrogen, they're kind of pulling the electrons towards itself. And that's making nitrogen more and more electron deficient and taking on a more positive sort of role in this arrangement rather than in an ionic compound. Any questions on that there? And lastly, here we have dichromate. Again, starting with our oxygen, which is -2, there are 7 of them, gives us a -14. Dichromate has an overall charge of -2. In this case, though, we don't have just one chromium, but we have 2. So in this case, each chromium needs to be +6. +6 and 2 is +12. +12 and -14 gives us a -2 that's left over. And in this particular case here, we end up with chromium as +6 and our oxygen here as -2. Any questions on how to assign oxidation numbers or states? Okay, so that is a good place, I think, to stop. And we'll pick it up next time, talking again how to balance some of these redox reactions. And then we'll get